Hi, I am Mr. Peck from Ideas Inc. School, and today we will be discussing about an aspect of forces known as work done. What is considered work done? Work is done when a force is applied to move an object, and this work involves the process of energy conversion. Due to the reasons stated above, work done is therefore defined as the product of the force exerted on a body, and the distance moved by that body in the same direction of the force. In short, the formula for work done is F times D. F being the force applied and D being the distance moved. Please note that because this is a physics formula, all units used must be in SI units. Thus, force must be in newtons while distance must be in meters. The standard international unit for work done is Newton meters or joules. However, there are strict conditions attached to this simple formula. Firstly, the force applied must be against a resistive force. This resistive force can be friction or air resistance. Here is an interesting tidbit. If a person throws a hammer in outer space, is that considered work done? The answer is no. This is because there is no resistive forces in space. Thus, even though a force was applied, no work is done. The same thing happens when you push against a very heavy object. Although a force is applied, as long as the object does not move, no work is done. The second condition involves the displacement of the object. The distance moved by the object must be in the same direction as the force applied. Lastly, the distance moved must be the most efficient distance in order to achieve the work done. Let's look at some examples listed in the notes. Please pause the audio to refer to the diagrams. Let's begin. The first example involves a person pushing a 3 kg box to the right using 50 newtons of force and over a distance of 3 meters. The work done can be calculated by taking the force of 50 newtons and multiply it by 3 meters to obtain 150 newton meters. This is known as the work done against friction. But why is the weight of the box not taken into consideration? That is because the force due to its weight is pointed downwards towards the ground. And since the box is moving towards the right instead, the direction of force due to its weight is not in that same direction, thus it will not be taken into consideration. The second example involves lifting a 5 kg box up a height of 1.5 meters. We will start by converting 5 kg into weight by multiplying it with the gravitational pull of 10 newtons per kilogram. Then the work done can be calculated by taking the weight of 50 newtons and multiplying it by 1.5 meters of vertical height to obtain 75 newton meters. This is known as the work done against gravity. But what happens if that person decides to walk 3 meters to the right after lifting the box? Will this add on to the work done? The answer is no. Because the person is simply walking horizontally and the height of the box remains unchanged. The work is already considered done, thus no additional work is done. The third example involves a person rolling a boulder up a 5-meter slope with a diagonal applied force of 30 newtons. The work done against friction can be calculated by taking the 30 newtons of force and multiply it by a distance of 5 meters to obtain 150 newton meters. We can do this because both the force applied and the distance moved by the boulder is in the same direction. The final example involves the person pushing the same boulder. However, in this example, the diagonal force applied is not given. Instead, the mass of the boulder is provided. We will first convert the mass of 2 kg into weight by multiplying it with the gravitational pull of 10 newtons per kilogram. Then the work done against gravity is calculated by multiplying the weight of 20 newtons with the vertical height of 3 meters to obtain 60 newton meters. We can do this because weight is a force acting vertically, thus we can only multiply it by another vertical distance of the same direction. Now we will move on to the final section of this chapter. In this part, we will be discussing Newton's second law. This law states that the resultant force experienced by an object is the product of its mass and its acceleration. Additionally, this force will act in the direction of the acceleration. In summary, all this is represented in the formula F equals m times a, where m is the mass and a is the acceleration. We will be considering 3 different types of forces acting on an object. Number 1, the force applied on a body, for example, engine force or a pushing force. Number 2, the resistive forces that the body experiences, for example, friction and air resistance. And number 3, the resultant force after considering the first 2 types of forces stated above. Next, let's explore the 3 different cases of motion. In the first case, when the force applied is greater than the resistive force, this will cause a positive resultant force in the direction of the applied force. Thus, the object experiences acceleration. However, when the object's speed increases, it will also experience a greater resistive force. This can be in the form of friction or air resistance. Thus, this will lead to case 2. In the second case, when the force applied is eventually equal to the resistive forces, the object is experiencing balanced forces. At this moment of equilibrium, two different outcomes can emerge. The outcomes depend on how the object is behaving initially. If the object has kinetic energy, meaning the object is already in motion, it will therefore continue to move at a constant speed. But if the object is initially stationary, it will continue to remain stationary instead. In the last case, when the force applied is lesser than the resistive forces, like when car brakes are applied or when a parachute is deployed, the object will decelerate until it comes to a stop. We have come to the end of the chapter. If you have any doubts, please approach Mr. Pat. Thank you for listening and have a nice day.